welcome to our Chapter 9 video. This video is going to cover section 1, 2, 3, part of 4, and 11. So the chapter is called Chemical Bonding 1, the Lewis Model. So of course we got to first just have our little introduction. The purpose of this chapter is to look at the shape of the molecules that they create. And then in chapter 10, we'll actually put names to those shapes. So for now, we're going to look at how those bonds are formed through something called, we're going to look at 3 different types of bonds: ionic, covalent, and metallic. Now we've talked about 2 of these a lot. Ionic is when we have a transfer of electrons. It's between a cation and an anion, which is usually a metal and a nonmetal, but we also know polyatomics can come into play. A covalent bond is when atoms share the electrons, and this is between 2 nonmetals. And then a metallic bond is one we haven't really talked about, and again in this chapter we're just going to briefly cover it, but it's metal cations in a sea of electrons. So we'll talk about that a little bit later at the end of the video. So before we look at the bonds, we have to talk about Lewis structures for just atoms individually. So we start by looking at the valence electrons. And in our last group of chapters, we looked at valence electrons and determined how to figure them out. And our quick way to do it is based on which column they're in the periodic table. So if they're a main group element, meaning they're in the S or the P block, they're going to have the same number of valence electrons as their column number. And if they're in a transition group, then we're going to use the S and the D electrons. So to write a Lewis symbol for an atom, we start by writing we write the symbol of the atom. This, of course, tells us that we're dealing with oxygen, but it's also representing the core electrons and the nucleus. And then we use valence electrons represented by dots going around the atom. We put 1 dot on each side, so top, bottom, left, right, and then we start to pair them. So the maximum that it can hold is 8, and this is a significant number for us. So oxygen has 6, so 1, 2, 3, 4, and now we start to pair them, 5, 6. So this is our Lewis dot structure for oxygen. Now I said that the most it can hold is 8, which we refer to as an octet. Noble gases have an octet. The exception is helium. It only has 2, so we say it has a duet. The goal of bonding, whether it's ionic or covalent, is to have an octet of electrons. So either done by sharing or by transferring. Here's our second row of the periodic table and all their Lewis structures. So notice that we go from 1 to 2 to 3 and so on until we get to neon with 8 valence electrons. Now what's nice is that the elements in the same column will look the same, meaning oxygen and sulfur's valence structures are going to look exactly the same because they have the same number of valence electrons. So moving on to some ionic. So we'll talk about ionic bonding in class, but on the video we're going to talk about lattice energy. Lattice energy is the amount of energy released when an ionic bond forms. So here's our structure of sodium cation bonded to chlorine anions. And notice that it's completely surrounded by chlorines, or we can look at it from the other perspective. Each chlorine is completely surrounded by sodiums, but this is going to make it very stable. It's exothermic, so as the energy is released, that's the lattice energy. That's the energy that we're going to calculate. So for sodium, it's negative 411 kilojoules per mole. We can't really measure this directly, but we can calculate it using some of the stuff we learned back in chapter 6. There's a few steps, 5 actually. We have to look at the energy associated with each of these steps, turning a solid into a gas, and then an atom into a cation, our diatomic into just a single atom, and then again our atom into an anion. And then the amount of energy it takes to put those 2 together, and then our lattice energy. So it's really just a giant Hess's law problem. This is the energy of the salt, the energy of formation of the salt. This is turning our metal into a gas. This is turning our non-metal into atoms, so instead of a diatomic. This is turning our metal into a cation, so we're using the ionization energies we talked about in our last chapter, and we would use as many as we need. So if it was a +3 charge, we would need 3 of them. And then turning our anions turning our nonmetal into anions, and so we use the electron affinity for that. And then all the way down here, this is the lattice energy. This is what we're solving for. So here's the same thing in graph form. Right here, this arrow is representing the overall energy, and then we have the metal turning into a gas, the diatomic turning into an atom, the sodium turning into a cation, chlorine turning into an anion, putting them all together, and then we get the overall energy for the structure. This step 5, the one that's the maroonish colored arrow, this is the lattice energy. This is what we're. So here are all the steps for sodium chloride. And this is showing us that it is a Hess's law problem. The sodium is a gas, the chlorine is a single atom, the sodium is a cation, the chlorine is an anion, all cancel out so that we get this as our overall equation. And this is taking all of these values and putting them into one math equation. Then we do a little bit of rearranging because the lattice energy down here is what we're solving for, so really we're just moving the rest of this stuff to the other side of the equation. Here's our numbers. Now we would look all of these up in the back of the book. If it was a test question, they'd be given to you. This is the one that we're solving for. We do multiply them by coefficients, so for chlorine it's a 1/2. Plug in our numbers, and for our lattice energy for sodium chloride we get negative 788 kilojoules, and that is kilojoules per mole. Now we can predict lattice energy based on trends. The lattice energy will decrease as the size increases because a bigger atom means that there's going to be a less of an attraction because there's more electrons in the way of the nucleus. And as the charge increases, the lattice energy increases. So as we have a +3 versus a +2 versus a +1, that higher charge will have a higher attraction, which means a higher energy. You can think of lattice energy as how much energy it would take to separate those ions. The more attraction, the more energy it will take. And then our last slide is the very last section of the chapter, 9.11, metallic bonds. Metallic bonds are kind of weird, and they don't really fit with what we've been discussing, so we have literally one slide and one small section on them. When metallic bonds form, the metals form cations, just like we normally see, but those electrons just kind of form an electron sea, and then the cations are like little islands in between. So it's really all you need to know about the metallic bonds. In more advanced classes, it's something you'll talk about more, but they don't fit with our big general trends. All right, that is it for Chapter 9. We will talk about ionic and covalent bonds in class. Thank you.